This field application testing has led to significant developments to compaction machine systems, including the development of Caterpillar's intelligent compaction systems. He is involved in the current FHWA DOT implementation and application of intelligent compaction as well as compaction training for asphalt paving crews. We're very grateful to have him here. As you've been through a few of these already, you know the drill. We've got a roll that will be passed around. It's important to sign up for that, especially if you've got a license for continuing education units. That's how that gets tracked. If you are from out of state and you need to have that as well, we've got a form you can fill out. So grab me after we're done, and we'll get that filled out for you. With that, I'll go ahead and turn it over to Brian. Thank you.
All right. Thank you, Scott. Welcome. Just to kick things off here, how many field engineers we got in the crowd here? Okay. Couple of you. Materials? Good chunk. All right. Very good. Well, welcome. Scott gave my bio. I'm with Caterpillar Paving Products, been with them for about 20 years, doing product development, application testing, and so forth. And so with that, I'm going to give you an overview of compaction, some of the principles. Might be basic for you at first. Then we'll get into some of the technology that we have on machines today, how it can be used to create longer lasting roads and better roads. First of all, what is compaction? Mechanical process of removing specified amounts of air voids. So on asphalt, you're looking at maintaining about a 7% air void. And you need that in there to maintain the structural integrity of the design. Through the compaction process, we're hoping to develop the structure you're looking for by developing machine on machine, or excuse me, stone on stone contact. This is what's building the strength to carry the loads. Normally, a fair amount of the compaction occurs right behind the paver, right off the street. So today's vibratory screeds produce compaction energy. There's also tamper and vibratory combinations that produce higher levels of compaction. Generally speaking, you'll find compaction right off the street somewhere around 85% dense. Depending on certain mix types, some of your SMAs, you could be in the neighborhood of upper 70%. When you're in that upper 70% compaction levels, you have a lot of work to do with your rollers. And it's important to understand the impact the roller can have and how to use the various aspects of the roller. Like I said earlier, starts immediately behind the paver. So you want to be on the asphalt when the asphalt's at its highest temperatures. Because the asphalt is a perishable product, it's cooling at a rate that you need to influence it to create the compaction as quickly as you can. It takes planning, it takes understanding your machines, it takes setup of your machines to optimize this compaction process. When you look at the costs occurred through this whole process, look at your aggregate, fairly high level of cost. Look at your asphalt. Bitumens, oils these days, they're fairly costly. Compaction is critical in being successful with the road structure, and it's actually a very low percent of the cost. But what it does is it brings very high value. So going back to knowing how to set your machine up, knowing how to prepare properly to produce the highest level of compaction results. So the forces in compaction, we have static pressure, basically weight on machines. We've got manipulation. That could be brought on by vibratory systems, could be brought on by a rubber-tired pneumatic roller. We have impacts, again, back to vibration. And then finally, the last is vibration, which is introducing dynamic forces. Looking at a steel drum, most of the rollers in the industry are tandem. Some are combi rollers where you're looking at a combination of steel drums and rubber tires. We're looking at the static pressure that these drums produce is a pressure per linear unit of measure. So a PLI, pounds per linear inch. That's the static pressure that these machines are rolling on the ground and actually creating compression based on that. If you look at our machine lineup, so you see a constant and growing static pressure as the machine weight increases. It's generally proportional to the mass of the machine and the drum width. So have larger machines, higher production, as we're sitting up here in our 79 and 84 inch. These rollers exert a higher pressure than smaller commercial rollers. Okay. So how do you know when you should be using a specific model or another? You'll be looking at your compaction widths. You generally want to have the compaction covered in at least 3 passes of the roller. Okay, so when we get up in larger highway projects here, you can see where we're not recommending using smaller rollers anymore, but generally using the higher production rollers. The pneumatic roller uses both static and the manipulation to create compaction. Static force is just simply by the machine mass exerting a wheel load, which actually applies the pressure to the asphalt layer. One of the highest levels of compaction pressure is exerted by a pneumatic roller. So it's important to have flexibility in machine mass. So we change our static pressures by changing the weight of the machine. It's also done by varying the internal tire pressure. So many pneumatic rollers on the market today have inflation systems. So you're actually changing the inflation pressure of the tires on the fly. So you change the machine mass, which is the actual pressure that it puts on the ground. Then you change the tire pressure, which actually affects the contact area. Okay? It's very important to have uniform tire pressure. The manipulation occurs with the combination of that machine static pressure and then the flexibility of the rubber tires. This exerts vertical forces, so forces generally straight down, but also in an angular nature. So it's not only like tandem steel drums are pushing pressure straight down, pneumatics actually do this through the flexibility of the tires. Mentioned earlier about the contact area and the effect of pressure of the tires. So let's take a look at this first example here where a pneumatic roller set with a lower tire pressure actually is producing inconsistent contact area of those tires. So you can see by the tire and the effect it has on its contact, and so you have higher pressures around the outside than in the center, and it'll end up leaving a wavy surface like such. Similarly, with too high a pressure, you have the inverse effects, and again an inconsistent surface. You also notice here when your tire pressure is too high, you lose your tire overlap, which is necessary to keep a smooth surface. And that's where having uniform tire pressure allows you to have a uniform contact area, the right amount of tire overlap, and a finished smooth surface. So a couple of things to look at when your pneumatic rollers are leaving tire marks and you can't get rid of them. Tire pressure is one of the first places to look. Make sure that you're uniform and you're in the proper tire pressure. I get a lot of questions on what is the proper tire pressure. Well, it depends on the mass of your machine. So here's a table. So we've got tire pressures across the top and we have wheel loads down the side. And you can see that tire pressure really doesn't affect the heaviest machine mass that much. Why is that? The reason for that is because the tire pressure and the internal air pressure has a hard time changing the contact area. It has a very hard time influencing that tire contact area, okay? Whereas some of your highest pressures occur at maximum tire pressure at the lightest machine masses. But when we look backwards, this is creating this scenario in the center where you have a very high contact pressure because your contact area is very small. Thus, it's going to yield a surface that is not smooth. So when we look at that again, you can find that about 90 psi seems to be a pretty happy spot for many machine masses. Okay? So if you're using pneumatics, consider tire pressure, consider your machine masses. Not always does the heaviest machine create the best compaction results. Now let's talk about impact forces, dynamic forces of vibratory drums. Generally, we're looking at vibration caused by eccentric weights inside a machine. Will create a dynamic force, which I'll talk a bit about frequency and amplitude a bit after this. But it's important to balance these forces so we're not creating overcompaction. Overcompaction creates damage to the bitumen. It also creates damage to the aggregates. So looking at the vibration simply caused by an eccentric weight. So you have an eccentric weight centrally located in all rollers that vibrate. This creates excitement that actually moves that drum. The drum moves at a specific frequency, which is tied to the RPM of the eccentric weight. The amplitude is a balance of that eccentric weight and the drum mass. So we're creating enough energy to lift that drum and move it and actually compress into the asphalt. And that's the dynamic nature of a vibratory system. Here's a graphic that shows amplitude. So amplitude is basically the distance the drum moves into the asphalt layer. So the more compaction that's occurring, the less that moves in there. And it's basically a self-regulating system. On breakdown passes, the drum will move the maximum distance into the asphalt pass after pass. That becomes less. Okay, and it's important to balance the amplitude setting you're using with the number of passes so that when you're creating compaction and you're using let's say a 4-pass pattern, at the end of that 4th pass, you're not actually entering into a decoupling state, which is where the drum is becoming airborne. That's where we have damage occurring, and oftentimes you can see the impact marks. Okay, it's either damage can look like white dusting of aggregates or you'll see the impacts. So it's important to balance this. So all of these factors here influence, depending one way or the other, the type of amplitude, the magnitude of amplitude that we should be using. You know, our layer thickness. If we're at 2 inches or less, we need to be in a lower force range. Greater than 2 inches, we can use higher forces because we have more material to absorb that energy. The base support, if we're on a rigid base, say we're doing a mill and fill, again a situation where you should be in medium to lighter forces. If you're on a flexible base, which would be considered an aggregate base or something like that, you can put a bit more energy into it because it's going to transfer into that base as well. Oil viscosities, when you look at modified versus non-modified products, they all have different curing rates, and it's important to use the energy to benefit and create your compaction as quick as possible. Crushed angular product versus just pit run aggregates takes more force to move angular aggregates. So round aggregates will tend to glide better with one another, especially when combined with asphalt. And then ambient temperatures. The cooler your ambient temperatures are, the cooler the base material is, the more energy you're going to need to use because of the irradiant factor of the cooling. So you need to get your business done on compaction before you move on. Frequency, on the other hand, that's the number of rotations that an eccentric weight creates. So every rotation will create what we call as an impact. So ideally, you want to have between 10 and 14 impacts per linear foot of distance traveled. So if your paving speeds are higher because you're laying a thinner lift, you need to be able to have a frequency on your roller that equates and ties and correlates to that paving speed. So matching paving speed along with a frequency on the roller is critical. This can be accomplished by either having a higher frequency on one roller or having multiple rollers on a job site. Give some examples a bit later of when to use multiple rollers. This is just kind of a guideline. You know, if we're looking at amplitudes that are greater than 0.8 millimeters, which is about 30 thousandths of an inch, you know, we consider that a high amplitude. Medium amplitudes are about, you know, 20 to 30 thousandths, and then 15 to 25 thousandths we consider in that low amplitude. Everybody's rollers on the market will give their highest amplitude at the lowest frequency. So frequency and amplitude are tied in that perspective. So then you ask me, well, what is centrifugal force? Why are we looking at centrifugal force? Simply stated, centrifugal force is a function of the mass, the rotating speed, a square of that speed, and the distance the CG is from the center of rotation. Centrifugal force is the force that is a measure of an eccentric vibratory system. Does not equal compaction force. So this is a critical thing to think about. Amplitude is what creates compaction. Remember that amplitude is defined as the distance that drum moves into the asphalt. Centrifugal force is a computation of the eccentric weight, how fast it's spinning, how big it is, and so forth. Amplitude takes into consideration centrifugal force as well as mass of the drum. Okay, and so it's a combined measure that actually creates the compaction result. So don't be fooled into thinking centrifugal force is what I need to create compaction results. Here's an example of one of our systems. So if you look at our amplitude here and our frequency, so here's our lowest frequency, 42 hertz, where our highest amplitude is about 0.78 millimeters, and then we're exerting 89 kilonewtons of force, okay? But when we change to our highest frequency, we're actually exerting more force with a lower amplitude. You may need to use higher force with lower amplitude and to get better compaction results. And it's just simply understanding those dynamics can allow you to develop compaction quicker. Here's an example. A machine, when I look at these two machines, which one would you think would generate better compaction results? So 0.6 versus 1 millimeter of amplitude, medium frequency versus low, same centrifugal force. Who says machine 1? Raise your hands. One taker on machine 1. How about machine 2? More takers on machine 2. I'm going to go with machine 2 as well, okay? Because it's that distance the drum is moving into the asphalt that's creating the compaction results. The centrifugal force is equal between these two, and so this is what creates compaction, is that amplitude versus centrifugal force. Now, the answer, number 1 machine, what we didn't talk about is what kind of a layer were we on. Okay, just simply looking at the machine, you would choose the higher amplitude, and that's generally right. If we were on a thicker layer, for sure right. On a thinner layer, maybe machine 1 was a good solution as well. Okay, so it's using a mix of them, of amplitude and frequency, can create compaction results. So optimum compaction occurs when you have a balance of your machine forces as well as your dynamic forces. When these forces get out of balance is when you create a decoupling state. And that's when machines will actually be bouncing, drums will double bounce, sounds like a bell ringing. You'll hear that sometimes on final passes because the compaction level is increased and the amplitude was set too high still at that time. Got some technology in a bit that I'll tell you about that. It's pretty exciting, that can change the way machines are looked at and provide better results. So as a summary, know how to use amplitude, know how to use frequency. Crews must understand how asphalt layers accept the force. Efficient compaction occurs when all the forces are in balance. Now let's talk about some technology that's developed in the asphalt compaction arena. Any questions about basic compaction before we move on? Okay. So I'm gonna talk a bit about what we call our auto-adjustable compaction system. So basically what this is, a machine that has built-in ECMs. So each one of these drums has a accelerometer, number one, measuring the forces that the machine's putting into the ground, taking consideration of the asphalt's response back, and then making a calculation, changing the amplitude on the fly. So you set your frequency based on your paving speeds. So you set your frequency such that your compactor is able to deliver the optimum compaction results. It keeps up with the paver. Then you push one button that says automatic. This system will automatically choose the right amplitude to deliver optimum compaction results. What will happen on pass 1 is we're delivering maximum energy. Pass 2, slightly less. Pass 3 and pass 4. Remember that situation I talked about earlier where you got to pass 4 and you maybe had a drum that was decoupling? This machine will never do that because it will back off the amplitudes so that it never decouples. Part of what that accelerometer and those ECMs are doing is they're actually measuring the potential to decouple. So it takes this machine right up to the point of decoupling, which is the maximum energy you can put into an asphalt layer, and holds it at that state. From pass to pass, it will slowly decline. So you produce the highest compaction results in the fewest number of passes. Takes the operator setup. It's as simple as pushing the automatic button. So now you don't need a foreman or a superintendent on the job site to set the machines up. QC guy just measures, yep, you got good results, keep rolling. This machine automatically will deliver the best energy. You figure out what your rolling pattern is, allows the operator to focus on driving the proper rolling pattern. Maximize the compaction with each pass, limiting damage from overcompaction, yet yielding the quickest compaction results. I mean, that's in essence what this machine will do. Pretty exciting technology. Now let's look at longitudinal joints, unconfined edges. I'm showing you some of our edge cutting technology here. So a machine can be equipped with either an edge cutting system or an edge compactor. Here I'm showing you this is an edge compactor. It's basically a 45-degree bevel that comes down, holds this material so that when the compactor runs along the unconfined edge, rather than the material moving out, it holds it in place. Thus it delivers better compaction results, better densities on that unconfined edge. Couple of videos here that can show you what these things look like in action. This happens to be one of our 67-inch rollers. This is actually on the Salt Lake City, Utah airport. So generally an airport has a spec where you have to cut the unconfined edge because the compaction is not there. This is an edge cutter in action. Pretty simple system. Simply just rolls along there, cuts it, come in with a skid steer and remove the material and lay your next pass. Precise control allows you to meet other cuts that are in place exactly. So a pretty neat system. Likewise, the beveling system looks like this. So here you can see it rolling, holding the material. So it's preventing that edge from pushing out. Great systems to use to generate compaction along an unconfined edge. And for intelligent compaction, a lot of things are going on in this space. Intelligent compaction, I look at it, it could be as, last slide, yep. Cutting is a additional process. So if you cut and remove, clearly you removed the lower dense product. If you put the bevel in there, what I can tell you is I will guarantee you an increase in edge density. I can't tell you that it's going to be the same as in the middle of the asphalt, okay, because it's going to depend on every one. But I believe if you put a bevel on an unconfined edge, you're in a much better spot than not putting anything on it, okay? Results?
Typically, you would be asking for 94%. And in this case, the edge, 100%.
Yeah. So the question was, on an unconfined edge, you know, if you're looking at an asphalt layer, generally you're looking at a density requirement of 94%. On an unconfined edge, you're saying it's 90 or 91. Will we be able to achieve 90 or 91? I think we have a good chance of doing that, okay? Can I give you an exact example? I think it's going to depend on every situation. What are you using for materials? How thick is your layer? How well does this wheel? So this bevel wheel, we make it so that it handles about a 4-inch layer. There are products that we offer that have lamination. So you want to size that thing perfectly to your layer thickness. The more perfect you can be, the better off you are, and the better you'll hold that material. To answer your question? So looking at the intelligent compaction space here, temp sensors at a minimum. Operators got to know what their asphalt temperatures are, what they're working within. If machines aren't working with asphalt temperature measuring systems, we're doing a disservice. We need to make sure that we're within a range that we can influence this material. All right, on a breakdown roller, not a problem, right? But it's when you're in that intermediate roller and finished roller. If you have not generated your compaction in the breakdown phase or the intermediate, if you're still using vibration in the end, it's critical to know when you shouldn't be. Okay, and temp sensors can help you do that. GNSS, Global Navigational Satellite System, mapping. This is basically taking GPS, tying it to a roller's location, keeping track of temperature map, as well as the pass count map. So this empowers the operator with a very good understanding of their rolling pattern, what they've done. When you have a target set up for 4 passes, how many times do you actually achieve that? Got a few examples here coming up that shows you it's not a common thing. Fact is, you don't know what you're not measuring. Okay? So when you're looking at echelon rolling, if you have rollers that are doing a pattern, they're acting as one, it's important to have machine-to-machine communication. Machine-to-machine communication will actually share this map. It allows the one operator to see the other operator's pattern, so they can actually coordinate their efforts to produce quality work. So an echelon breakdown pattern might have 2 rollers that are doing one pattern. If they're equipped with mapping equipment, they must be sharing that data, or they simply don't know where the other's at. Here's another quick video. With a crew here, right here in Utah.
The compaction results have improved based on, we've been able to kind of track our rolling patterns. You get a more uniform densities throughout your mat. You're not getting over compaction here and, you know, under compaction there. Also with the temperature sensors on them, being able to know where your optimum rolling temperatures are. It's improved the communication between our roller operators based on they can see where each other's been.
It tells me how many patterns I've done, and it tells me whether or not he's doing all his or not. And I like that because there's a lot of times we get in a hurry and he has to hurry up and move up. And if we're not getting compaction, I don't know why, but I can look at that and see that he minus to pass, so then I need to pick it up.
It's a very simple system to run, very simple to set up. The nighttime operation would definitely be beneficial in my opinion. Obviously it's dark, sometimes you kind of lose where you've been. You can't really see your watermark during the night, so that way you kind of know you are getting your full coverage and you haven't missed a foot section somewhere. My experience with it has been very helpful, so I do definitely believe it helps the efficiency and productivity. I've been very pleased with it.
So a good example, you heard what she said. We have to catch up. How often does that happen? Any idea? Again, we don't know what we're not measuring, right? I would beg to say on every job that happens. Here's an example of what a map might look like. So this is taking data from a machine, importing it into a graphical interface called VisionLink. Caterpillar and Trimble. We use VisionLink for our machine health displaying as well as our project data. So compaction data is something that's viewed through the project tab. Here's a typical rolling pattern. Okay, so you have some transition areas. Okay, tells us, you know, somebody might be able to do some post-processing analysis on this and just pull this line and say, all right, this rolling pattern was 429 feet long. Estimate that. Is that right or wrong? I don't know. I can see this next one was a little bit longer just by the map. I can also see that this transition's a little bit different. Okay. This may be a bit excessive on the roller compaction here on this transition versus the next. This one's leaner yet. Maybe there's an area there where we missed a section, we only got one pass. So the way you interpret this, a red color represents one pass. The green is 2 because we set our target pass here of 2. So basically what an operator needs to do is just color the screen green. Okay? Set the right number of passes, set your target at whatever it needs to be, paint the screen green. When you go over those passes, it turns purple. It might even turn black or different colors depending on how many passes were actually created at this location. Is this the right length? Might not be. I think I'll show you in a bit that it might not be. Here's a temperature map. So you can see this is superimposed on Google Earth. The compaction job was right here. It was a night job. This was in California. Rest assured, this was not in Utah. So your roads are perfect. This was in California. All right, so these lines out here are what are drawn around the job to create a project boundary. So we set our minimum target up here at 225 degrees, maybe a little bit high, but nonetheless gives us that intermediate space. So here it tells me that 61% of this was under 225 degrees when the final compaction roll was done on this. Is that right? Is that wrong? Don't know. Maybe density was met on this whole project, or it wasn't, okay? I don't know all those details. I'm simply analyzing this from a temperature perspective. So when we zoom in, we're able to look at this in a little bit greater detail. What do you see consistent about each one of these patterns? I see a final pass that's blue. I see a final pass that is at a low temperature. So go back to that length of that rolling pattern. Was it right or was it not? Maybe we needed a shorter rolling pattern. Maybe we needed another roller. Okay? And you can look at this. Again, you don't know what you're not measuring. As intelligent compaction, fundamentally, I think our jobs need to start seeing temperature and pass count mapping. Minnesota DOT is moving to 100% intelligent compaction on asphalt by 2018. The reason they're doing that is if they find a core that missed density, what do? They go back to the map. Almost every time it's a rolling pattern error. An error might be a missed spot, it might be too few passes. Again, you don't know what you're not measuring. Now let's talk about a CMV. What is a CMV? It's a compaction measurement value. It's basically a composite value read by an accelerometer on a drum, so vibratory forces create the first harmonic. The way the earth and the sublayers respond to that are picked up by this accelerometer and expressed in what the industry calls as a CMV, or compaction measurement value. Another quick video here. This just simply shows you, the sound in this one, simply shows you what a CMV measurement looks like to an operator while he's rolling. Also shows you a pass count, shows you a temperature alert. This is what a temperature and pass count with a CMV measurement will look like. But notice how that CMV number jumps around a lot. Is 55 a good number? Is 60 a good number? Don't know. Okay? And we can know what our target should be, and it's going to be somewhat lower than that. We would need to measure it and look at the overall job and figure out if we set our compaction level at this point, this represents 90% of the job. It's at 10% that's below that I think we need to concern ourselves with. Why? It could potentially be undercovering a failure of subbase. Mill and fill, we're grinding, we're recycling, we're doing a cosmetic fix. If we had failures caused by substructure failures, it's only a matter of time before those resurface. If you're just skinning the top and putting a new asphalt layer over it, whatever failures were below that will remain there and will show through in the asphalt layer after a couple of years. Can we agree on that? Okay. So in this case, I'm looking at that same job. Oh, sorry. Question? Yeah. Yep.
What was causing that? Is that related to base issues?
Variation in everything. Okay, the vibratory forces are your first dynamic. Okay, that's going to be very consistent. The forces that go into the ground and how the ground responds to them are a function of the stiffness below that hole. You know, in this case, that was on a completely rehabbed road that it had intelligent compaction all the way up. So it might be varying moisture levels. Whatever is going to absorb the forces below that asphalt layer are what's going to affect that. We simply can't tell you that this thing measures 6 inches and measures 12, you know, because the stiffer the material, it could be measuring 3 feet down because the forces travel that far.
Is it a function, though, at the end of the job to how well it failed?
So the question is the CMV value correlatable to the performance of the asphalt layer? And the performance of the asphalt layer is a function of everything below it. Okay, and the CMV will give you a measurement and an indication of the stiffness of a whole layer. So if we were to go back to that video and watch that number, we're somewhere around 45 to 60. There were some 20s, some 30s in there. Those are the areas we need to worry about. And so to take a accelerometer measuring system and tie it to the density of an asphalt layer cannot be done. It will not predict the life of that layer of asphalt either.
But it does throw up a red flag that there's something else that's possibly
Potentially, yes. So it can throw up a red flag, and let's look at these areas in a little bit more detail. So what was done on this map is we simply filtered out the CMV above a certain point, and so we end up seeing some bleed through or some softer areas. I don't want you to draw any correlation to the cracks in the asphalt that are there before. There could be some value in that, but I think it's presumptuous to assume that just simply looking at it. Okay, it was concrete, fair. Thank you, Aaron. And so let's look at that in a little bit greater detail. So we can zoom in. When you have data that you've measured, you recorded something, you can actually take a look at it and analyze it. With a cursor, you can pick on that point. It tells us the CMV summary is 84%. Is that 84% dense? No. Correct. It's 84% of whatever that target number is. In this case, I know this job had a target CMV number of 35. So the CMV in these areas is below a 28. Okay? I believe that this is indicating substructure variation. Can I tell you that it's a failed substructure? I can't. Simply because I don't know how deep that reading went. That's some of the development that we continue to do, and we don't have the answer to that right now. So if I was to drop a core right there, I still might see a passing density. But 5 years from now, I could see a failed road there as well. And I think that's the value of measuring a CMV, is for historical reference to look at future failures. Exactly. If you measure a CMV, you might be able to come back to this 5 years later and say, yeah, we're failing here, and we saw a lower CMV in that area. We measured, I mean, you could simply go to this and measure with a nuke gauge and figure out, yeah, we met density there. But density of an asphalt layer doesn't guarantee that its structural integrity is there. I mean, I think you have the best chance. Yes, sir. I couldn't agree with you more. His point was maybe we should put that on the subgrade before we put the asphalt on. Absolutely. Okay? Now, if you're doing a mill and fill, I'm not going to advise that you vibrate with my roller across a hard surface and try and figure out what the CMV of it is. I think California is trying to do that. Please don't do that in Utah. Because it's wrecking the roller. And what are you learning from it? You could be decoupling the roller and you're getting a false reading out of all of it. Because that accelerometer is tied to that drum. If that drum's double bouncing, it's producing an erroneous reading. Plus wrecking the roller. And your asphalt layer, because you just added more cracks to it. Right? That's kind of the part of managing your frequency and your forces. The beauty of this, it's got northern and easting. You can take a GPS rover right to this exact point on the road and find where this soft spot is, precisely where this spot is at. You might see failures reflecting through that you won't need to do that anyway, but I can't guarantee you that either. It might be just fine. Lastly, our good friends Larry and Aaron at Wheeler Machinery locally here can hook you up with experts up at my location that can come out, help you with understanding intelligent compaction, figuring out what should be done. FHWA is still studying that. They're going to do it for this final year. I think they will go through 2016 as well. I simply believe that having a temperature and a pass count measuring is a big step forward. Big step forward and actually tied to that specific asphalt layer, not substructure. You know, because you're not going to dig up all your roads and redo the base. Let's be honest with each other here. But it might be indicative of some some sub-failure. So simply looking at compaction factors, you have project design, you have mix design, layer thickness, aggregate type, mix temperature, climate conditions. All this stuff comes into creating in your ability to deliver compaction. A couple of things I want to promote here. We got a couple of apps. One of them is a production calculator. This one actually talks about trucking, paver speed, compaction, takes into account the entire paving train. If you're paving too fast at such a speed that you have to wait for trucks, you're not doing yourself a justice by stopping. Pave at a slower speed that your trucks can keep up. You're all limited by your plant capacity and trucking, so tie your paver speed to that. Same time, you can figure out what you need for compactors. This app tells you how to manage a paving job site. Lastly, there's also a app for creating amplitude. What amplitude should I set this roller at as a base? Okay, and this is going to provide you with your operators, foremen, your contractors with a guide, so that you can set up a machine properly. You might be able to increase that amplitude, or if you have that automatic system, just put it in automatic. And Larry and Aaron have one of those too. Some things that, climate conditions, high ambient, low base temperatures, low ambient. You got to adjust the rolling pattern accordingly, okay? Pay attention to these things. Not every job has the same rolling pattern. The work that you get done in that initial phase is critical. Most of the compaction is generated in this phase of the paving train. If you have to wait till your final roller to generate your compaction, you're going to have a hard time getting it, because the bitumen is set up and it's close to setting and you're running out of time. Get it done on the initial phase and you'll be in a much better spot. Use amplitude to drive results in that space. Sometimes maybe you might even want to consider throwing a pneumatic roller in that breakdown phase. Putting very focused high pressures on that asphalt can yield results. Makes a mess. I'm going to be very upfront with that. But the tandem rollers behind that can clean it up. Couple of general housekeeping things here. Never stop rollers on the mat like that when they're hot. Why? You can see what simply the water systems have done. You're guaranteed to have a bump in that location. Paving process starts with good paving practices followed by good rolling practices to generate smooth roads. Best paving practices can be screwed up by rolling operators that don't know what they're doing. When you have to stop and fill with water, which everyone does, plan it. Make sure that your trucks have the appropriate hose length so that you can either do it on the shoulder or turn out or something. The operators, quality control, they must understand the forces of compaction. Gather the proper information up front to plan your job. Evaluate the work, measure, make adjustments, and then be consistent. Uniform compaction starts with consistent driving habits. That's it. Any last questions, comments?